Very good, Walter, and welcome. Hopefully, you can hear me well. I wanted to extend a welcome to all our guests, and I see a couple of our colleagues from Washington, D.C., DOE Office of Environmental Management are joining us as well this afternoon. So I think I saw John Moon and JP Pavon. Thank you for joining us and supporting this event, the Tech Talk. So if I miss anybody, please forgive me. But again, everybody's welcome. And as Walter mentioned, there will be some times for question and answers toward the end of Roger's presentation. So it's my pleasure to welcome and to introduce Roger, Mr. Roger Boza, or as I like to call him, Dr. To be, Roger Boza, Mr. Roger Boza. And Roger, before I go through your bio, I would also like to recognize and welcome one of our former DOE fellows now working for the NNSA. I think I saw Silvina Di Pietro dialing in. So she's joining us as well from California. So Silvina, welcome back, welcome home. And I'm glad that you were able to join us as well. So Roger received his undergrad degree, his bachelor's in computer science with a track in software engineering from Florida International University, 2018. And I believe we immediately grabbed him and convinced him to pursue a PhD degree, which he's currently doing. So Roger is pursuing a PhD degree in computer science with a focus on machine learning, artificial intelligence, and deep learning techniques that are reflected as part of the work that he's conducting at the Applied Research Center as part of the DOE Fellows Program. So Roger is directly working with Dr. Himanshu Upadhyay in this area as a DOE Fellow. And he was formally inducted as one of our DOE fellows back in, when was it, Roger, 2018, 2019? But it's been a pleasure having him as part of our program and conducting research in this very important area. He conducted summer internships at Idaho National Lab, I believe 2019 timeframe, and he's been doing that ever since. So every summer, Roger has a permanent duty and job to work with our colleagues at Idaho National Lab in very, very interesting projects. So I think the last couple of internships there have been virtual, but nevertheless, he has made great progress in terms of some of the projects that INL has for him every summer in the area of machine learning, deep learning, artificial intelligence. So, and I think some of that is perhaps reflected in his presentation or topics very, very close to that as part of his DOE Office of Environmental Management research that he's conducting at the Applied Research Center. The last thing I'll say, so I don't take too much time, is that Roger and also together with an international team of STEM students from various countries, they took the International Atomic Energy Agency, the IAEA Young Professional Challenge. So they took that challenge and they proposed the concept of integrating robotics with machine learning, artificial intelligence, to facilitate the decommissioning of nuclear facilities across the world. And that team placed tab 3. So tab 3 from, I think, about 28 countries that submitted proposals, and the team that Roger and also one of our other DOE fellows, Daniel Martin, led, they were placed on top 3 teams, and that was presented by then this past November, December at the IAEA, Decommissioning Network Forum that took place toward the end of last year. So with that, Roger, it's a pleasure introducing you. I'll turn the floor over to you.
Thank you, Dr. Lagos, for that kind introduction. Good afternoon, everyone. I'm really excited to be here today on the KMIT platform, giving this tech talk about crack detection and localization using deep learning techniques. This type of technology is state of the art, and I hope everyone here enjoys the information I'm going to be sharing. So let me get this. All right, so a little bit about me. Like Dr. Lagos introduced me, my name is Roger Boza. I'm currently pursuing my PhD in computer science at Florida International University. And my main areas of interest are artificial intelligence, machine learning, and deep learning. Within this domain, most of my research is centered on computer vision for anomaly detection, object detection, and image classification. I have been a DOE Fellow since November 2018, and I have interned 3 consecutive years at Idaho National Lab. Pretty much I have a permanent job over there by now. They really like the work that we do together. The first year I worked on doing some process anomaly detection to help predict mechanical failures of equipment currently used to cool the air in the drywall area of nuclear reactors. So that was pretty significant. The second year, I created a computer vision module for the route operable unmanned navigation of drones that allowed it to fly indoors without GPS signal. That was really interesting. And the third year, which was this past summer, I worked on 3 projects simultaneously that needed imagery data analysis and predictions. The first one was Firewatch, the second one was obstacle avoidance for drones, and the third one, gauge detection. So the work that I will be presenting here today was done at the Applied Research Center located at FIU, and it was under the mentorship of Dr. Himanshu Upadhyay. So, all right, let's start with some background information on the problem set. So as you can see here, many of the facilities around the Department of Energy complex were built more than 50 years ago. In many cases, these facilities have exceeded their expected operational lifetime. In other cases, the facilities have been placed in a cold and dark state where they remain inactive, just awaiting decommissioning. Now, while those facilities are waiting to be decommissioned, it is necessary to understand the structural health conditions of the buildings, mainly for safety concerns. In any of those scenarios, the structural integrity of the facilities may have been compromised, which means that adequate inspections and data analysis must be performed on a continuous basis. And that type of monitoring and maintenance in nuclear infrastructures poses many challenges in dismantling buildings around the DOE complex. The structural health monitoring is imperative to the ongoing surveillance and maintenance across the DOE complex. Machine learning and deep learning techniques are proven technologies that can facilitate the assessment of structural integrity in these aging facilities. This research focused on investigating specific applications of artificial intelligence to solve those DOE EM problem set and challenge areas, including potential applications of existing state-of-the-art technologies to assess the structural integrity of the aging facilities. So our objectives were very simple. Number 1, to develop artificial intelligence and machine learning solutions capable of doing structural health monitoring of D&D infrastructures. 2, identify and monitor cracks in D&D structures with real-time processing. That was very important, was critical. And 3, optimize the models to achieve high performance and low false positive. And lastly, deploy the trained models on mobile devices. Now, with those 4 objectives in mind, we had 4 research goals that we created to explore the problem set and build solutions. The first goal was to perform anomaly detection. This task answers the question of whether there is an anomaly in the data or not. And this was solved by using convolutional autoencoders. The second goal was to perform object detection. And this helps answer the question of what anomaly is and where is it located. We tackled this problem using convolutional neural networks, more specifically YOLO version 3. The third goal was to detect cracks in imagery data. Now, the second objective aligns perfectly with this task because a structural crack on a surface is considered an object during analysis. The last goal was to deploy the trained models on mobile devices with a real-time application for surveillance and monitoring. This will put the technology developed at the fingertips of the operators who need it, and in my opinion, that is the main goal for this research. Now, before we dive into the research details, I want to cover some basic information about artificial intelligence that is needed in order to understand the research in this presentation. Additionally, I would like to clarify what autoencoders are and how convolutional neural networks work. Don't be frightened, I'm not gonna get complicated, and I promise not to show integrals, differentiation, Jacobians, Bayes theorems, and the whole mathematics behind all of this. This is just gonna be an introduction to it so that we can understand the work that is at the end here. So there are two tasks normally done in computer vision. They are anomaly detection and object detection. For us to successfully achieve them, autoencoders and the convolutional neural networks were used to create mathematical models capable of solving the challenges. Now, the following slides will introduce each one of them along with their variations and their capabilities. So let's start off with the anomaly detection. What is anomaly detection? Well, according to Wiki, and the most common definition is that anomaly detection is the identification of rare items, events, or observations which raise suspicions by differing significantly from the majority of the data. Now, there's a couple of synonyms for anomaly detection. They all end up doing the same type of task, like outlier detection, noise in the data, how many deviations a point is away, novelty detection, exceptions, etc. But I think a picture is worth 1,000 words. And if we look at the image on the right, this one right here, right, we can see there's a whole bunch of eggs and only one of them is red. And as humans, we can definitely find out which one is anomalous in here. I mean, it sticks out like a sore thumb, is this red one. But for computers, that's not so easily done. We don't just analyze colors. We actually take context into account. So, definitely AI is used to help tackle this problem. Now, when we talk about anomalies, there's different ways that anomalies get interpreted and the problems that they translate to. Some examples are structural defects, which we can see here in the top left image. Medical problems is used, to detect anomalies in, MRIs, CAT scans, and things like that. Errors in text, this is commonly done on this software called Grammarly that helps you write a little bit better. It's also used in bank fraud. If something stands out, a transaction that you normally don't do, just execute it. So anomaly detection is used for all of these types of analysis. Now, there's 3 types of techniques using machine learning to do anomaly detection. The first one is unsupervised anomaly detection. Then we can do supervised anomaly detection, and lastly, semi-supervised anomaly detection. The first one, which is the unsupervised anomaly detection, that deals with detecting anomalies in an unlabeled test data set, meaning we have no idea what the classifications are, and we have no idea what the anomalies is. And it typically goes like this. We have a data set. In this case, just for example purposes, we have a couple of dogs, we have a bunny, and we have a porcupine. And we can use clustering algorithms to categorize and group these objects into similar ones. We can see here that the unsupervised learning typically will output a cluster with just dogs, a cluster with bunnies, and a cluster with porcupines. Now, the idea here is that similar data gets clustered together and the anomalous data will get clustered by itself. But we never told it what the original data looked like, what it was, its classifications, and we did not tell it how to look for the anomalies. We just interpreted that the lowest cluster is the anomalous one. Right. Then we can go to supervised anomaly detection. This one is a little bit more hands-on. For this one, what we do is we have our data, but we actually label it. We go to each data point, in this case the dogs, and we label it as dog. We label the other dog as dog, but everything that is not a dog, right, we'll categorize it as another class. For example, not dog, not dog. And what we do is we pass this to a machine learning algorithm, usually a classification one, such that given this image is supposed to predict duck, and given any other type of images, it predicts not duck. This is very effective as long as we have labeled data, and sometimes that is very hard to come by. And the last version of anomaly detection can be done through semi-supervised anomaly detection. This one is a little bit more complex. It's like a hybrid between the two of them. we start out with some raw data. Partially, the data gets labeled like duck or no duck, and a neural network or a machine learning algorithm is trained on that data. And what happens now is some of that data, right, the new incoming data goes in through the trained neural network and is predicted upon, so it labels it, but we also use some of the unlabeled data, and we pass forward those two to another algorithm that is supposed to learn from it. And the way that we know that it's anomalous is when it fails, when it has no idea which class it is and it gets it wrong. Now, moving on to object detection, which is the other task that we're really interested in. And this picture here in the background is actually one of my favorites, because when we do object detection, what we're trying to do is to find an object in an image. And typically to find that object, what we need is some sort of fingerprint, some features that are unique to it for us to be able to find it and classify it. So more formally, what is object detection? Well, according to Wiki, is detecting instances of semantic objects like cars, buildings, humans, but specifically in digital images and videos. Now, the notion here is that every object class has its own special features that will help it in classifying it afterwards. What does that look like? So on the right here, this is a sample image with a couple of apples. And object detection has to do two things here for it to be successful. First, it has to localize, in other words, find the location of the objects. And we can see that by this yellow bounding boxes on each one of those apples. But it has to go a step further. It actually has to tell me that within this yellow rectangle, there is an apple, which will be its classification. Now, there are some techniques to do this. There are some non-neural approaches. One of the two most famous ones are SIFT, which is a scaling variant feature transformations, and HOGs, which are histograms of oriented gradients. Nothing special about them, but what we will actually end up doing is the approaches that deal with neural networks. And for that, we have a large variety of them. We can have region proposals, we have single shot detectors, which are very fast. Unfortunately, they're not very accurate because there's a trade-off between speed and accuracy there. We have networks like RetNetNet, deformable convolutions, but this one down here at the end is you only look once, the YOLO protocol and architecture. That's the one that is of main interest because of its speed and its accuracy. Now, moving on to autoencoders. So what is an autoencoder? Well, the word itself is composed of two terms, auto, which is short for automatic, meaning working by itself with little or no human control, and encoder, which means to convert into a different form. In our case, it's going to be converted into a particular form because we're using binary encodings right here. So the autoencoder, what they do is typically an artificial neural network used to learn efficient data codings in an unsupervised manner. And we kind of already touched up on what unsupervised is. So I never tell it what I'm giving it. I just parse the data through it and it's able to do something with it for me unsupervised. Now, at a fundamental level, an autoencoder learns to copy its input space to its output space. And I'm going to show some images of what that looks like and what it means. The copying process is not perfect. Right? The encoding is a lossy process, and approximating the input means that we only preserve the important features. So the combination of these two properties of autoencoders leads us to something very unique, which is actually part of the research. I'm going to show that later. Now, the typical uses for autoencoders, they're used to reduce dimensions on a data set. Typically, this is done when you want to analyze the data and increase performance differently. You can also do it for feature learning, extract what was important about the images, discard the rest, reconstructing signals. So you can imagine a signal coming into your system, but some of the data got lost, some of the bits got flipped, so a part of the image might be missing. An autoencoder, since it can map an input to an output, which is itself, it can recreate that data for you quite successfully. And it's also used for creating generative models. Those are, models that can generate data for you synthetically. Now, what do autoencoders look like? Well, there's mainly two parts. We have the encoder, which is this left-hand side of the image right here. And then we have the decoder, which is the right-hand side. And the whole process is to, given some input on the encoder, it will compress it down to some sort of code. And then from that code, we can uncompress it, we can decode it back to its original form. If the network is able to do that successfully, then the code that we have here is a compressed representation of the original data, and that has a lot of benefits. What does that actually look like? This is a typical dense neural network expressed as an autoencoder. We notice here that the input layer has more neural connections than the second, and the second has more than the third, and so forth into the middle, like a chokehold. And then it's the exact opposite. It's like a mirror image of the left side to decompress it. So we can start out with an image like this kitty right here. By the time we get the information passed to the latent variable, which is a chokehold, exactly at the middle, this is the encoding, the code for it. It might not look like a cat anymore. It might start looking like the features that were important for that cat. But given those features, we can go in the opposite order and we can reconstruct the original image. Autoencoders, they come in 4 different variations. The first one is a sparse autoencoder. Nothing very interesting about this one. It just helps you generate data a little bit different, like introduce minor perturbations. We have denoising autoencoders. These ones are amazing for removing noise in the data. Contractive autoencoders, these are really nice to learn a mapping function that is robust when your data seems to be a little bit corrupted. And then lastly, we have variational autoencoders. And these guys are really good because they generate data from within this distribution, but the data doesn't necessarily have to equal or be like the one that it was trained on. Now, moving on to convolutional neural networks. Definition. So the name, abbreviated typically as CNNs, starts with convolution. And a convolution is a mathematical operation. Typically, it involves combining 2 functions to produce a third, so nothing fancy there. We have the word neural, which it's relating to the nervous system. But when we're dealing with computers, and in the terms of this research, neural is for the components designed to mimic the human brain. And we have the word network. So officially, a network is an arrangement of connected components. In our case, it could be a group or systems working together. So convolutional neural networks, what are they? They are a type of artificial neural network, and I think that doesn't say much about them, so let me explain. Artificial neural networks, and specifically the CNNs, they're the most common type of neural network used to analyze imagery data because of the convolutions, which I'm going to explain and show in the next couple of slides. They're composed of convolution layers. Those layers are the building blocks of the CNN, and they contain the learned kernels, and I'm going to show what this is as well, which are the weights, that are capable of extracting the features which distinguish one image from another or one object from another. And the links in the CNN, they represent unique kernels, which is exactly what we need to extract the meaningful features and be able to create predictive models. So this is a typical example of a CNN. This one in specific is Google's GoogleNet model. It looks a little bit overwhelming. It looks convoluted, but all of the components are here. So we have the convolutions, and there will be these blue nodes that we can see in the graph. And they're the ones responsible for doing that mathematical operator of combining 2 things, 2 mathematical operations to get a third. The neural part in all of this is the activation functions, which are inside of each one of those on their output segments, and network. So when you consider this whole graph right here, everything is connected, and thus we have a network of connected nodes. And that's how we get the name convolutional neural network. Now, I mentioned that I was going to go briefly into what those kernels are. So the convolution, which is those two mathematical operations to produce a third, is exactly what we see here. We have some data, and since we're talking about images, this could be the red channel information, the green channel, or the blue channel in the RGB file. And what we have is this kernel right here, which is a 3x3 matrix of numbers that if we convolve those numbers with the original image, we're going to get a set of data that is a little bit different. And the idea here is that once we train the network, can we get some numbers, a set of weights right here, such that when it convolves and it produces this new one, this new set of data, we can use it to classify the image or find objects in there that are of interest. And the excite operation that is happening between this kernel right here, this matrix, and the image itself is just the element-wise dot product. So it's multiplying the first number on the kernel with the first digit of the window that it falls in, plus the second number on the kernel times the second number on the window, so on and so forth, until we generate this set of numbers right here, which if we interpret this as another image, it's what we mean by extracting the features. This is going to start highlighting different parts of the image, and it's going to start destroying other parts of the image. And normally they work like edge detectors that can find vertical lines, horizontal lines, circles, and things of the sort. Now, normally at the end of a convolution layer or a convolution block, which is multiple convolution layers one behind the other, we have another layer called max pooling. And this is done to reduce the spatial dimension of the problem. So sometimes we have data, in this case images, that are in the orders of thousands of pixels by thousands of pixels. So we have in the order of millions of data points going into this convolutional neural networks. And if we just pass that information layer by layer by layer and it never reduces, we will have untractable solutions that don't compute very fast, very slow, and take a really long time to learn. So one thing that we can do is we can create this max pooling, which is an idea that, given 4 neighboring pixels, this is pixel information, we pick the highest. And what it does is it generates a new image, which is a quarter of the size, but contains the features that were most prevalent on it. And between all of those 4 things that I just mentioned, now we can actually get to the research and the fun part, because we have all the components already. We know what a autoencoder is, we know what a convolutional neural network is, and we have our 2 tasks, anomaly detection and object detection. So the first research goal, which is anomaly detection, what are we going to do exactly with that? Well, we first start out with an image and it has a crack. And what we would like to do, what we would like to have is an image like this one on the right. So given this image on the left, pass through our model, some model, in our case is going to be the convolutional autoencoder, we want to be able to highlight all of the anomalies. And the anomalies in this case will be interpreted as the crack itself. So how do we achieve that? Well, we start out with a convolutional autoencoder. So this is the merging of both of those technologies, of merging autoencoders with convolutional neural networks. And the reason for that is that the convolutions are very effective at analyzing the images. And we have imagery data, so it makes sense to use convolutions. And autoencoder, because something very interesting happens. If we train this network with a baseline data, meaning images that do not have cracks, and it learns how to map it, in other words, it learns to map the initial image, compress it, and reconstruct it again, then something interesting happens once we give it an image with a crack. And I'm going to show what that looks like in a couple of images. But this is the actual architecture, and we can see here that we start out with the same space, the same size as the original image, and little by little we're making it smaller, until we get to the latent space. So this is the encoding of it, and it contains a very small amount of numbers. In this case, just 128 numbers can generate this image right here again. So the data set that we used was composed of 3 individual sets. The first set were images collected from an open source repository that had over 20,000 images, so we used some of those. The second set is from the first outdoor test facility. So at ARC, we have an outdoor test facility with a wall that resembles the DOE complex and some of its surroundings. So we took some of those pictures and we trained it with it. And we also then transferred and got some more data from a second outdoor test facility wall to make up an entire data set. And the way that we split the data in order to train and test and validate the model was using the 80-20 rule for this. Now, once we trained that model, and this is a graph of the performance of it while it was training. So what we see here on the x-axis is the epochs, and that is just the iterations that the network is seeing the data and learning from it. So 1 iteration, 2 iterations, 3 iterations, all the way up to 100 in this case. And on the y-axis, we have the loss. In the case of this autoencoder, the loss function that was used is a root mean square error, because we need to know the difference between the original image and the one that we reconstructed. So the more those pixels differ from each other, the higher the error, and we can capture that with a mean square error. And we can see here that the network started out learning, and this is just one of the training sets that we did. It started out learning, it found the local minimum, then it jumped out of it. It got a little bit worse, but as it tries to learn, it found another better minimum, meaning it can predict and recreate the data better. And it kind of stayed there after about 10 to 15 epochs, and it didn't progress anymore. So we were comfortable saying that the autoencoder learned how to map its initial space, those images, into itself. So this is the reconstruction capability. The original data looks like this top row. So it's just, small images, they're sliced, cropped out windows from concrete slabs, granite, multiple surfaces. But the one thing in common is that none of them have a crack in them. The second row is the convolutional autoencoder reconstructing each one at a time. And we can see here, it's a little bit small, but there's a small little rock in this picture right here, and it reconstructed with it. There's some minor details on some of these pictures, and they get reconstructed. Not perfectly, like we stated at the beginning. Autoencoders are a lossy process, but that's what actually helps us. So this third row is the error calculation. If we were to get the reconstructed image and we subtract pixel-wise the first image, we get this new image. If the pixels match, their subtraction is 0, and 0 in an image is viewed as black. So what I'm looking for here is, the most amount of black as possible. So this was actually a pretty good data set it was able to learn with very minimal error. Now, why is all this talk about the error and the autoencoder being able to reconstruct the data important? So here's the idea. If we give it this image right now that has the crack and we pass it through that autoencoder, it doesn't know how to reconstruct the crack properly. It has never seen it. So when it tries to reconstruct this image, it is going to reconstruct the parts that it knows very well, but the crack itself is going to start failing. It's going to start merging it. It's going to start smearing it, blurring it. It's going to do a whole bunch of things to it, except reconstruct it accurately. So now what happens is, if we subtract the first image from this one, there should be a lot of error in the area of the crack. And that's exactly what we need, because we can put a threshold on that error. And if it passes a certain value, then we know that that was anomalous. And since we're interpreting those anomalies as cracks, we can determine where the crack is. Now, the third row right here is a visualization of exactly that. And if we can see, it definitely gets us all the edges, right? There's very low false positives. And in all of the training samples that we did, the validation samples and the testing samples, it was able to perform kind of like these images that we're seeing here. But one thing that we noticed was that these detections right here contain a little bit of noise because we're doing it at a pixel level. So we applied a technique, which is a Gaussian filter, to the output data, to those errors. And what we get is a cleaner merging of where the anomalous areas are. And I'm going to go back and forth really quick between these two slides so you can see the difference between them. Right? It looks very noisy, doesn't look concise. And then all of a sudden, we can start highlighting the crack a little bit better with more precision. This is a plot of the performance metric. So since we were analyzing each one of those pixels as anomalies, and then we applied that kernel filter to remove some of those noise values, we're able to reduce the amount of those point anomalies. And that's what this chart is showing. On the x-axis, we have, the image. So image 1, image 2, image 3. And on the y-axis, we have the total number of groups of point anomalies. And we can see that without using the reduction technique is the blue line. It's way higher, almost twice as high as when we used the reduction, and we were still able to find those anomaly sections. So at the end, when we put all of this together, what we have is kind of like a pipeline. We load the image, which contains a crack. It tries to reconstruct it. It's not going to be able to do it properly because it doesn't know how to reconstruct those cracks. It's going to compute the difference, right? We're going to subtract image 1 from image 2. We're going to get the error. To this error, we're going to apply the kernel, the Gaussian kernel, to remove some of those point anomalies. Then after we apply the kernel, we use the dynamic threshold to, above a certain number, we actually consider them as anomalous. Below that, we remove it. We consider them as normal. We grab this image now, we convert it to grayscale, and the reason for that is so that we can do a heat map coding for it, which looks just like this in image number 7. And what we can do now is overlay this heat map over the original image to have our final image. And it looks phenomenal. It looks fantastic that it was able to highlight where the crack is. Now, moving on to research goal number 2 and 3. And this is the one that deals with object detection. So what we have here now is an image, and what we want is for the solution, the neural network, to tell me how many cracks there are in this image and where are they located. So remember that is done by identifying, putting a bounding box around the object of interest and labeling as a crack. So given the image on the left, we want to get through some AI model the image on the right. Now there's 2 ways of, actually 3 ways, sorry about that, of doing object detection to locate individual cracks in an image. The first technique is called sliding window. The second technique is called region proposal. And the third technique is called YOLO, which is the one that we implemented. The first technique, sliding window, the oldest, is the most naive, and all it does is you crop out a section of the image on a fixed width and height, and what you do is you start sliding that, right, cropping here, and you move the croppings left, and right, and every time you make one of those croppings, you ask the neural network, what do you think is inside of that? And if it tells you the object, then you're done, you found it, but you got to keep going. Now, you can picture that if we have a high resolution image in the order of thousands of pixels, and we have a small window, let's say 100 by 100, you're going to be analyzing thousands and thousands of smaller images, each one of them through a neural network, just to try to find out where those objects are. So in conclusion, this one is very slow, right? It's the slowest method available, but it has the highest accuracy, because once you find that object, you can make the sliding window a little bit bigger or a little bit smaller, and you can fine tune it to get its exact location. The second approach is with something called region proposals, and that starts leveraging the convolutional layers, but it does one pass to create a feature map. Once it creates this feature map with the convolutions, it creates a region proposal network, which is just what areas of the image are of interest, and make a prediction of what object was in there and how big it is. So this type of approach definitely performs a little bit faster than the sliding window, but since we're making guesses where the objects are when we check, it drops in accuracy. Now, the last approach, which is the YOLO, you only look once, specifically version 3, is the fastest. So it's called you only look once because you only need to pass the image once through the entire network, and it will make all the predictions. It will find all the objects that you want, and that it got trained for, and it will label them. So this has the fastest accuracy, and YOLOV 3 is a little bit old. YOLOV 4 and V5 have already been released with a little bit faster performance, and they started fixing the drops in accuracy. So at the moment, YOLOV 5 and V4 actually both perform the fastest and have almost the highest accuracy. Now, once we decided to go with YOLOV 3, we need to label the data in order to train the neural networks. And what do we mean by that? So before, given an image, I would have told it if there was a dog, a cat, an animal in there. But now we need to tell it more information. For every object, every class that we want, we need to define 5 parameters. So we need to tell it the center of the object, and that center has to be relative to the image width and the image height. And the centroid is defined by the X and Y coordinates of the pixel. We need to tell it the relative width and the relative height. That makes it 4 parameters. And we got to tell it what type of class this is, which is the object itself. Now, imagine having hundreds of pictures with hundreds of items and objects, and you have to manually go and analyze, this picture has 1,000 pixels by 500 pixels, and I think the middle is right here, and that is pixel 220 by 119 relative, and you try to compute all of this manually. This is a very intensive labor process. And thankfully, there's a tool that can be used to help with this, which I'm going to be showing soon. So for training this YOLOV 3 model, we grabbed and collected 51 images from an open source data set. And the images look kind of like this column of images right here on the left, which had a nice distribution of different types of cracks, different types of surfaces, and different types of environments. And the tool that we use to label this is another open source tool, very fast and user-friendly. It's called ImageAug and label IMG. And what it does is you load the image, you put a bounding box, right? So you manually select, well, the crack is from this point, this corner to here. And you just, draw boxes around all of your objects. And on the back side, the tool is computing the relative width, the relative height, the centroid, and you just tell it what class it is. And it saves a file with all that information. So this definitely streamlined our research analysis. Now, when we started with 51 images, that's not enough to do deep learning. We need a little bit more. And one way of doing that is using data augmentation techniques. One of those techniques is called affine transformation. And what we do is, given an original image, we can, sorry about that. Where did my presentation go? Technical issues, give me 1 second. There we go. Sorry about that. We can do translation. We can scale an image, means make it bigger, make it smaller. We can rotate it between some degrees, or we can skew it. So what this does is increase the amount of data points that the neural network gets to learn from, but it doesn't change the data distribution. So performance increases marginally with this type of technique. Now, there's another technique that we use in combination with that, which is a knowledge transfer technique. And what that does is it uses previously trained models that can share the useful information they learn and thus require less data for training. And the model that we used for that was the DARTnet 53 weights, which got trained on a data set called ImageNet. And that data set contained over hundreds of thousands of images with 1,000 classes. Now, unfortunately, none of those 1,000 classes were of cracks. They're mainly of other, objects of interest, like cars, airplanes, humans, laptops, water bottles, and things of that sort. But the idea is that once that network learns, a lot of that information can be used to learn and detect the new cracks. So we train the model in 2 phases. The first phase will freeze the main body of those preloaded weights, and the only layer that changes is the end, the new one that is for finding the cracks. And we train with this coarse tuning until we get to an acceptable level. Now, once we get to that level, we switch to the second phase, which will unfreeze the full network and it starts fine tuning. And this is where it makes minor adjustments and some nudges to the network to try to increase the quality of the prediction and the accuracy. So some of the hyperparameters that we use to train the model, we used a grid size, a grid search for it, because we have a batch size, and that is the number of images analyzed at a time before we update the connections and the weights in the neural network. The epoch count, so that's the amount of training iterations, whether we train for 10 iterations, 100 iterations, 500 iterations. The confidence score, which is how confident the model is with the prediction. That's a hyperparameter that we can change to get more detections, better detections, or drop out the detections that the network made, but is not so comfortable believing that it's the correct one. And lastly, we had the intersection over union, which is when multiple predictions are made for the same object. Only the highest one that would overlap with the original bounding area is the one that we are interested in. So what were the results of this? Well, if we look at the image on the right, we can see that in this image there's two cracks and there's a black bounding area. That is the one that is done manually. That is the perfect one. And ideally, that's the one that we want to get to. So the early models that had no optimization, no data augmentation are represented by this green one. We can see that it's a little bit loose, it overcompensates, it captures the crack, but it's capturing more information. We want it to be tighter, we want it to be closer to the black one. So then we moved to the blue one, which is after we did some initial optimizations, and we started with the data augmentation technique. And it started pointing the network in the correct direction. It's getting closer towards the original one, to the ideal bounding area. And then finally, when we compensate and completed the data augmentation using the other technique, which is the knowledge transfer as well, we can see that it is the best model that we were able to get. And it's this yellow one right here. And it's pretty close. I mean, this is not a perfect model. And most of the time, we don't find that the best ones, that they typically tend to memorize instead of generalize. So one of the side effects of generalizing into a good solution is that we have small margins of error. And in this case, and in this implementation, that can be viewed by the bounding area being a little bit loose around the ideal one. So moving on to the fourth research goal, and this is the one that puts all of this technology at the fingertips of the users, the people that need it, the people that will benefit from using artificial intelligence adapted to their domains. But this is not an easy thing to do. And let me explain why. When we create and train these models and we analyze all of this, we start with an operating system, typically Windows. We have a Python distribution, which is called Anaconda, to host and execute the programming language. For this case, our programming language of choice was Python, but we need something to create the neural network graph and handle all the type of layers, the convolution layer, the max pooling layers, the activation functions. For that, we used one of the most popular backends, which is called TensorFlow. But TensorFlow natively is very difficult to use, is very convoluted. It needs a lot of details just to get a minimal network up and running. So we can wrap TensorFlow with a library called Keras, which has helper functions to help you integrate and communicate with TensorFlow during the graph creation and thus the creation of the neural network. Now, once we have all of this installed, running together, communicating perfectly with no issues, we took care of all of the versioning controls, and we trained the model that we want, we end up with this right here. We end up with a file that has all the weights and the instructions of how the model works and what the outputs are. So what we need to do now, what we want to do is grab this model and put it on a mobile device running on a different operating system and on a graphical user interface. So that is quite a challenge and is not easy. One way to achieve that is to use something called TensorFlow Lite. And what that does is, once we have the final model that is trained, and that's the one that we want to use, we have the TensorFlow Lite backend that can run on Android apps, it can run on iOS apps. But the specific process goes like this. We have our model. TensorFlow has a converter to the light version of it. So it grabs the model, it grabs the weights, and it streamlines them so that they make a smaller footprint and they're easily runnable on mobile devices. So it goes through this converter, it creates a file specifically for that, which is the .tf lite file. And with this model now running the TensorFlow Lite backend on Android and iOS, we can execute the model instructions and get our predictions. This is still missing the GUI, so you would need to use a developer, an integrated developer environment for that. But the main connection going from desktops and servers to the mobile phone is this package right here, this backend called TensorFlow Lite. So what are the steps to achieve that? We train and tune the model on desktops, servers, if they're available, GPU servers, whatever we need. Now, once we have that model that we want, we save it for the TensorFlow Lite. So that goes through the converter and it exports the file that can be run on the mobile device. We build the GUI for the mobile app. We load the model into the device, and then we use the GUI to start making predictions and processing the information as needed. What does that look like? This is a picture that is worth 1,000 words again. In this version of the app, we have an iOS device, activates the camera, took a picture, and in this case, it runs the TensorFlow Lite model, and it makes a prediction of where it thinks the crack is, and it displays on screen that it detected one crack and its location. So what are the benefits of having a mobile app, besides the fact that we put it at the fingertips of the operators that need to use it? Well, it can make the detections and it can catalog them. It can save the data for historical reasons, and it can build an archive that can be queried later. So that is very powerful. That is beneficial for record keeping purposes. So what are the future works for this project and solutions? Go to next. Well, we want to start incorporating the testing models into the mobile app. So not just one solution. We want to put in there the convolutional autoencoders, our classifiers. We want to put in there the object detectors. So we want to be able to streamline every model that we have, convert it into its TensorFlow Lite version and deploy it. We want to begin adapting a trained model for the mobile deployment. That's exactly what I just described. This is more of a technical thing. We want to be able to detect smaller cracks, and that is an actually hard thing to do, because since we're using convolutions and to make the solutions tractable, we reduce the space as we go layer by layer using those max pooling layers that I mentioned. But if you recall, every time we do a max pooling, we cut the space down to 1/4. So by the time we get to the end on a very deep neural network using the convolutions, small objects tend to be lost and there's no information about them. So there's some things that we can try to do to alleviate that, to be able to detect the smaller ones, like making detection at different scales. And the other thing that we want to do is, now that we can find the cracks and we know where they are, right? We don't just want to say it's a crack. Maybe we want to start saying what types of cracks they are. They're hairline fractures, they're stress cracks, or any other type of crack that exists there. Not a civil engineer, but I'm pretty sure there's more than those two types that I can think of right now. So that's the direction that we want to move this research into. Okay, so lastly, I want to make my acknowledgements. The DOE FIU Science and Technology Workforce Development Program, specifically Dr. Leonel Lagos. Thank you for the kind introduction again. Dr. Ravi Gudavali, my art mentor, Dr. Himanshu Upadhyay, my major professor, Dr. Nagarjan Pavlikar, and our sponsor, which is the U.S. Department of Energy, Office of Environmental Management, under the Cooperative Agreement. And that concludes it. Any questions?
Right on time. Just couple of minutes to spare.
I practiced twice to finish right on time.
Roger, just a great presentation, great topic. So thank you for presenting and sharing your knowledge and your research with the rest of the team here, and our guests, right? Our guests from DOE. They had to jump off a little earlier because they had another meeting, but we had at least 3 DOE headquarters colleagues that joined us, and of course Silvina as well. But I do have to jump. I have no questions, just congratulations. I do have to jump to another 3 p.m. call, but again, great job. Thank you, Roger.
Thank you.
Thank you, Roger. Before we go, I want to open the floor to any questions that anyone who has to Roger, or any final comments. I'm not sure if you're still on the line. Do you have any final comments or closing comments?
Yeah, sure. Roger, great presentation. And this was one of the first AI machine learning project that we did with DOE headquarters under cooperative agreement. So thanks to DOE headquarters for giving us an opportunity here to develop this area of AI machine learning focused on image processing and applying different algorithms to solve classification and object detection problem. Roger, can you talk about, in addition to the crack detection, how we can use the object detection technique to address different problems in DOE EM?
Yes, for sure. So what I presented today, right, was object detection adapted to crack detection. But that's not the only thing that it can do. If you recall, we did a knowledge transfer by using a pre-trained model and changing the last output layer of the model for crack detection. But that can be modified to be able to find fire extinguishers, ladders, other objects of interest, fume hoods in a chemical lab. And all it would take is, a couple of hundred of images with the objects that, of interest, and we can retrain the models to be able to find it and provide the same solution, with very minimal effort.
Thank you, Roger.
Yeah, you're welcome.
Anyone has any other question that they want to ask here?
A quick question, Roger. This is Aparna. Very nice presentation, great presentation, of course. And you gave us all the important insights into this. We're trying to solve a similar problem under the work that we are doing here. In my task, I'm working on the corrosion detection in pipes and transfer lines, waste transfer lines, basically. And they are more related towards the type of material, type of corrosion. So I'm assuming that we can apply the same thing. I'm trying to work with one of my students. I'm sure you're helping him out as well from the machine learning aspect of it, wherein we want to see a new pipeline, carbon steel, stainless steel, different pipelines. And then I want to detect the onset of corrosion, the propagation of corrosion, and when is it time to replace it, or how much time do we have the remaining useful life of the system? So yes, so I'm assuming we can use similar trends, similar processes, right?
Correct. Yes. So there's actually like 3 or 4 things that you can do with that. One, you can train autoencoders the same way we did to find those cracks. So you give it all the data that was good, that has no anomalies in them, in this case being corrosion. And if it learns how to recreate that, once you give it a file, an image of an object that has the corrosion parts, it won't be able to generate it correctly. So you do the same technique. You can subtract those 2 images and it will highlight all of the areas that contain the corrosion. So another thing that you can do is train a classifier, right? Let's say that you had 1,000 images of corrosion objects and 1,000 images that have no corrosion. We can train a CNN classifier to tell the difference, discriminate between the 2 of them. Now that approach doesn't tell you where the corrosion is, but that will be, depending on what you want. Do you need to know where the corrosion is, or do you just need to know that there's corrosion in the image that you're looking at? And for the third one, to be able to, predict the remaining useful life of the equipment, you can do some type of forecasting, meaning give it the image of what it looks before corrosion and give it the image of what it looks like after corrosion. And we can get a neural network, and in this case will be another convolutional autoencoder to predict from the real one uncorroded into the future one with corrosion. And we can put parameters in there to justify for the time. And if it learns, it converges, when you give it a new image, it might be able to predict how long before it starts being corroded, and then you can take action.
Perfect. Thank you. We'll reach out to you again. Thank you.
You're welcome.
Well, thank you, Roger, again for your presentation. I want to remind everyone that in the chat there are a few links. One is to a feedback form. Please fill it out. It helps us to find the next topics. Also, if you're interested, the next Tech Talk is scheduled for April 19. We finalizing the topic, but if you want to stay in tune, please go to the website. Also, the link is in the chat. And you can find information about the previous websites, previous Tech Talks, recordings. You can sign up to a newsletter so you might be informed. You get new emails about upcoming Tech Talks. If there are any comments or questions, one last shot. If not, I want to thank again Roger for his presentation. Very well done. Congratulations. And thank you everyone for joining us. Hope to see you then next time. April.
Thank you everybody for being here and participating.
Thank you.
Bye.
Bye, guys. Thank you.
Bye.
Good job, Roger.